Module 4, Lesson 22, we're continuing with working with expressions, but now we're going to look at expressions with exponents. So we're going to first look here. If you have a piece of paper and you begin folding it, it's going to have you predict how many times, how many pieces there would be when you fold them. So I'd like you to rip out a piece of paper from your notebook or from, you could use loose leaf paper, any of that's fine. And so, first of all, it says predict how many times you can fold a piece of paper in half. And so my prediction is I'm going to say 20. Then, before any folding, there's only one layer of paper. So we have one layer of paper. See, just like this. There's no unfolding, nothing. This is recorded in the first row of the table. Fold your paper in half. Record the number of layers of each paper that results. Continue as long as possible. So 0 folds, 1 layer of paper. Number of paper layers written as a power of 2. So 2 to the power of 0 equals 1. Any exponent to the power of 0 is 1. No matter what our base is, if the exponent is 0, the answer is 1. So its number of folds is 1. So take your paper, fold it in half. If you look at it, you have 2 layers of paper right there, 2 layers. So number of paper layers, there are 2 of them. And so that's 2 to the power of 1, which equals 2. So this means that I folded it 1 time, which gave me 2 layers. So 2, it says fold it again. So when I fold it again, take a look. That is 1, 2, 3, and 4 layers. So if you span it out, you can see that's 4 layers of paper. And so that's 4 layers, which would be 2 to the power of 2, because that's 2 times 2, which gives you 4 layers of paper. You fold it again. So my 3rd time folding it. If I take a look at the layers, that's 1, 2, 3, 4, 5, 6, 7, and 8 layers. So that's 8. And that was folding it 3 times, which is 2 times 2 times 2. Fold it again. Check my layers here. That's 1. Nope, I think let's see. That would be 2, because over here, I don't know, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But if I turn it over here, that's 1, 2, 3, 4, 5, 6, 7, 8 on this side, which means there would be 8 more on this side. Just with the folds, you can't see that. So 8 and 8 is 16. And that's 2 to the power of 4. So that's 2 times 2 times 2, 16. If I fold it again, I look at the side that I can count, which it doesn't look like I have any sides that I can count, just the way that it's falling. So let me look at our pattern here. 1 fold, 2, 3, 4, so I can keep going. This is 2 to the power of 5. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And if you look here, you can see every time it's doubling. So we went from 1 to 2, 2 to 4, 4 to 8, 8 to 16, 16 to 32. This would go to 64, that would go to 128, and that would go to 256. So that's 2 to the power of 6, 2 to the power of 7, 2 to the power of 8. Are you able to continue folding the paper indefinitely? No, because I couldn't fold it small enough. Now, if we had like a special equipment, then we could, like a machine that could fold it tinier and tinier and tinier, but I couldn't. And it says, how can you use a calculator to find the next number in the series? You could either double the number of paper layers, or take 2 to the power of how many folds. Then you would be able to determine it indefinitely, which means forever. So C, what is the relationship between the number of folds and the number of layers? Folds is the number of times we multiply 2 by itself. How is this relationship represented in exponential form of the numerical expression? This right here is letting me know that I need to write an expression. So it's 2 to the number of folds equals my layers. If you fold a paper F times, write an expression that shows the number of layers. So we have 2 to the F equals my number of layers. Number 3, if the paper were to be cut instead of folded, the height of the stack would double each successive stage, which means each time after the next. And it would be possible to continue. Write an expression that describes how many layers of paper result from 16 cuts. So cuts are the same as folds. Okay, so I can use my first expression, which was 2 to the F. So we would take 2 to the 16th, which would be, evaluate this expression, writing it in standard form. So we have 2 times 2, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times. Now, because of what I've done over here, I know that to the 8th is 256. So I can go all the way to the 8th. We have 4, 8, 16, 32, 64, 128, 256, 256 times 2 is 528, I think. 512 wasn't even close. 512 times 2 is 1,024. 1,024 times 2 is 2,048 times 2, 4,096 times 2, 8,192 times 2, 16,384, 32,768 is then 65,536 layers, which is a lot. So look how quickly it grew. First it went from 4 to 8 and then to 16. then to 32, then to 64, then to 128, then to 256, to the 500s, then to the thousands, then 2,000, 4,000, 8,000, 16,000, 32,000. So look how the first number ended up being close to the same. So we have 4, 8, 16, 32, 64, and 128, and then 25, and then we have 51, then we have 102, 20, 40, so then we have 4, 8, 16, 32, and then it just keeps going. 65, which is close to 64. So when we're going exponentially, it grows very, very fast. So this is where, this is actually how we can see the flu spread. And so one person gives it to 2 people, and then each of those people give it to 2 people, and then all 4 of those people give it to 2 people, and then all of those 8 give it to 2 people. You have 16, and this is actually how quickly an epidemic would spread. As that every time somebody passes it on, they give it to more and more people. So bacteria are single-celled organisms that reproduce in a couple of different ways, one of which is called binary fission. In binary fission, a bacterium increases its size until it's large enough to split into 2 parts that are identical. These 2 grow until they are both large enough to split into 2 individual bacteria. This continues as long as growing conditions are favorable. So like when you're sick. So let's look down here at this one. So we're looking at, this is what scientists would do that study an infection or study an epidemic that may be happening somewhere. So for example, when Ebola spread, they had specialists go in. Down here at the very bottom, you had all these thousands of people that were infected, and they actually had to work backwards. They had to find out who was the first generation of person who had it, so then they could figure out how to prevent anybody else from contracting the disease. So if you use your calculator, you can just continue to take 2 times 2 times 2. So 2 to the power of 3 as you know is 8. And you write 2 to the 3rd. So now we're going to take 2 to the 4th. You get 16. 2 to the 5th. You get 32. And it's 64. And then you get 128. 256. 512. 1024. 2048. 4096. 8,192. 16,384. So then they ask you questions about it. So how many generations would it take until there were over 1 million bacteria present? So what you'd really need to do is continue this on, because it's an exponential growth and it doubles every single time. And so you could just keep going. So we have 14 right now. That's 15, 16, 17, 18, 19, 20. So we would need 20 generations until there were over 1 million present. Under the right growing conditions, many bacteria can reproduce every 15 minutes. Under these conditions, how long would it take for one bacterium to reproduce itself into more than 1 million bacteria? So we know that there would be 20 generations to be over 1 million. So the first generation was 15 minutes. Second generation was 30 minutes. So what I'm taking is my generation times my minutes. Right here, every 15 minutes, this is going to be times 15. Well, we had 20 generations, so it's going to be 20 times 15, which is 300 minutes. Now ask yourself, how many minutes are in an hour? That's 60 minutes equals 1 hour. So in 3 hours, it's 180. In 4 hours, so you can just do your table really. And I'm skip counting by 60 here and by 1 on this side. 4 hours would be 240 minutes. 300 minutes is 5 hours. So it would take 5 hours for bacteria to grow to 1 million. Write an expression for how many bacteria would be present after G generations. So this here and this here means you're writing those expressions with a letter. And so this would be 2 to the power of G. Looking over here at example 3, you have this box has a width of 3W. The height of the box is H, is twice the width, and so H is equal to 2W. The length of the box, L, is 3 times the width, so L is 3 times W. And that is the width, the height, and length of the rectangle prism are in the ratio of 1 to 2 to 3. For rectangular solids like this, the volume is calculated by multiplying length times width times height. So we take length times width times height, and like we did last week, we replace our letters with the equivalent value, 3W times W times 2W. We take out the pieces that we can multiply, so our 3 and our 2, so you get a 6, and then we have a W times W times W, which is W cubed. So that gives us the expression we'll use to solve it. So V equals 6 times W cubed. So my W is 1. So V equals 6 times 1 cubed. 1 times 1 times 1 is 1. And so it's 6 centimeters cubed. Now this one, I have 6 times 2 cubed. So that's 6 times 8. You get 48 centimeters cubed. 2 times 2 is 4. 4 times 2 is 8. This one, you have 6 times 3 cubed. 3 times 3 is 9. 9 times 3 is 27. So that's 6 times 27. 6 times 27 is 162 cubic centimeters. Then we have 6 times 4 to the third, which is 6 times 16. 6 times 64, I'm sorry. (384 cubic centimeters. And then our expression belongs here at the bottom. Volume is 6W cubed. So what I want you to do is go ahead and work through number 3. There should be a table. So the athletic director has created a phone tree that is used to notify team players in the event of a game. The phone tree is initiated when the director calls two captains. So we have Captain 1, we have Captain 2. During the second stage of the phone tree, the captains each call two players. Player, 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 player. During the third stage of the phone tree, these players each call two other players. So this is player 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the phone tree continues until everyone has been notified. If there are 50 players on the team, how many stages will it take to notify all the players? Now, keep in mind, this is stage 1. 2 players have been notified. This is stage 2. That's 4 more players have been notified. And so really that's 6. And then I continued counting from the previous one so that I would know all of the players in total, and that's 12. So we have the number of players plus the captains. So you have 4 players plus 2 gives you 6. We have 12 players plus 2 means we have 14 people notified. And then you're going to continue this tree and say, how many stages do we need? Or you could use the exponential form, so you could draw it out. Or look at our previous pages, seeing how you can determine the expression. So what expression would allow you to see in total how many people have been notified altogether? So remember, this is not figuring out how many is available in each stage. It's going to be how many has been notified altogether. And they want to know when that number gets to 50. And when you're finished, go ahead and let me check it, and we will. I can move you on.